So guys, welcome to this tutorial. In this tutorial, you have to determine the values of bending moment and modulus of sections of composite section. So this is a beam and steel composite section. The question is, a composite timber and steel section is as shown in figure 4. Calculate the maximum safe uniformly distributed load that the section can carry when simply supported over a span of 3.5 meter, given the following information. Permissible stress in steel is 150 Newton per millimeter squared, and permissible stress in timber is 7 Newton per millimeter squared. The modulus ratio M is 20. So from the section you see, steel sections measures 150 by 20 millimeter, while timber section measures 200 by 150 millimeter. This is how we shall proceed. Now here, what we are going to do, we will have to transform the composite section into equivalent timber, then analyze it, and then after that, we convert it into an equivalent, we transform it into an equivalent steel section and analyze to see which UDL will be able to be withstood by the structure without exceeding the specified stresses. Now we shall start with the transformed equivalent timber section. Now, because it is timber we are dealing with, the timber section which measured 200 by 150 will not change. It will remain with the same size and shape. What we are going to do is to transform or to convert the steel into equivalent timber section. And remember, from the modular ratio of 20, it means if I have area of steel, it will be equivalent. If I want to have an equivalent timber section, it must have an area 20 times that of steel. For this case here, we had two steel sections, which was 20 by 150 millimeter each. So if I multiply by 2, I will get the total area, and then I multiply by 20 because modular ratio of 20. So for a 6,000 millimeter steel, I will need an equivalent of 120,000 millimeter of timber section. And then remember, we said in terms of a geometric section, I section is the most efficient structural section. That is why we are arriving at this. Now, when you look at the top and bottom, we have steel. Now what we had as steel has been transformed to timber, but now with measures of 3,000 by 20 and 3,000 by 20, so that the total area should be equivalent to 120,000. How did it come about? It came about because originally steel was 6,000 millimeter square. Then we multiply by 20 millimeter, 20, which is modular ratio, to get an equivalent area of timber that will be able to carry or will have the same value as the steel section. Now, this is the section we have arrived at. So we have a section, we have top, middle, and bottom. Now, when you look at this section, this is a asymmetrical section, and our interest will be IXX. And we know that if we want to compute IXX, it means we shall compute Y bar. For it being a symmetrical section, Y bar is basically a half of the section from the bottommost line. So which is 20 plus 200 plus 20 divided by 2. So our Y bar or centroidal axis passes at a distance of 120 millimeter from the bottom. And then we have divided, we have section 1, which is the flange, top flange measuring 3,000 by 20. Section 2 is the mid section measuring 200 by 150, and section 3 is the bottom flange measuring 3,000 by 20. Now, we will proceed and calculate. Now, the modulus of this section is equivalent to, not modulus, but moment of inertia. For the entire section is equivalent to the moment of inertia of each of the three sections added together. And you know, by a parallel axis, to calculate the moment of inertia, you take BD cubed over 12 plus area multiplied by the distance from the centroid to the center of the section being considered, then squared. Now this will imply for the case of section 1, Ixx1 will be equivalent to, now since we are considering the x-axis, we only cube that dimension that is perpendicular to the axis being considered. For section 1, it is 20 that is perpendicular to the horizontal, or rather the x-axis. So 3000 times 20 cube over 12 plus the area, this is area, 3000 times 20 into bracket. Now, the y1 for section 1 is 20 plus 200, which is 220, plus 20 over 2 into halfway of section 1. That's why we have 230 minus 120 squared. We end up with 78, blah, blah, millimeter power 4. And then Ixx2, moment of inertia for section 2. Look at section 2, the narrow section. First of all, we said D is the dimension that is perpendicular to the axis of reference. So I will have 150. This 150 is the measure of thickness times 200 is the vertical distance, 200 cubed over 12, then plus, this is the area of section 2, 150 by 200. This section 2, its y, its center is 20 units plus 100 over 2, plus 200 over 2, which is 120. So 120 minus 120 squared, which will give us 1 million millimeter power 4. And then the moment of inertia for section 3, remember section 3 is the bottom flange, will be 3000 times 20 cubed, because we are cubing what is perpendicular to the axis of reference, divided by 12 plus 3000 times 20, that is area. But the height to center of this section 3 from the bottom is just 20 over 2, which is 10 minus 120 squared. This will give us 728. 0.0000 millimeter power 4. Then from there we shall compute the total moment of inertia by summing up moment of inertia for section 1, moment of inertia for section 2, and moment of inertia for section 3, where we shall end up with this 155.60000 millimeter power 4. And then we know that stress is given by moment multiplied by y divided by the moment of inertia. I remember for maximum moment to occur, for the maximum stress to occur, it means this y is the distance from the neutral axis. Now, looking at this beam, you find now that the centroidal axis is passing through the center of this section here. So both the value of y is equal both on the upper and lower part of the neutral axis. So in this case, the y, which is 120. So I will substitute. Now, because I used the timber section, I will take the stress permissible for timber, which is 7. I will take 7 is equivalent to moment, which I don't know. I multiply by 120, which is my y. We calculated here the centroid, divided by the value of moment of inertia we had, 155.60000. So I will find that my moment will be basically 90.8 kilonewton meter. I've converted it from this one in terms of Newton millimeter. You divide it by 10 power 6, because 10 power 3 will convert Newton to kilonewton, and then another 10 power 3 will convert millimeter to meter. So it will be 90.8 kilonewton. Now, we are told this is a simply supported beam. Now we want to compute the UDL. We know that the maximum moment for a simply supported beam carrying a UDL is equivalent to UDL times L squared over 8. So we equate 90.8 is equivalent to UDL, we don't know, times 3 squared, which is the span. We are told span is 3. squared divided by 8, from which now if I make UDL the subject, I'll get the value of UDL is 59.3 kilonewton per meter. That is case 1. Case 2, I'm going to transform it into an equivalent steel section. Like I told you now, for the case of steel, the equivalent area of steel, when I convert a timber to steel, it is equivalent to area of timber divided by 20, or rather divided by the modular ratio. So timber had a section of 150 times 200. Now I divide that area by 20, which will give me 1,500 millimeter squared. Now that is why, and you see the timber, the two steel section will still remain at the top and bottom. Now what has come in between is the timber. We are just maintaining the structure like it is initially. We have timber in between, sandwiched between two steel plates or steel bars. Now here, we'll find that since we have only one timber section and it has an area of 1,500, and we have to maintain that span of 200 vertical. Now the thickness of this steel now is 7.5. Remember this steel, the 7.5 times 200 steel is what has come from 150 times 200 timber section. Now we shall proceed as we did. The figure is symmetrical, which means the y bar will be 120 from the bottom, 120 meter from the bottom. And then if I want to compute the area 1, I assume the top flange, it will be 150 times 20. Then y1 is the vertical distance from the bottommost line to the center of section 1. It will be 20 plus 200, which is 220 plus 10, which is 230. Area 2 will be 200 times 7.5, and then y2 will be, from the bottom will be 20 plus 200 over 2, which is 120. And then now area 3 will be 150 times 20, and then y3 will be the measure of 20 over 2 because you measure from the bottommost line. So moment of inertia for section 1, as we said, because we are the I-axis, it means reference axis is x-axis. We only cube what is perpendicular to the x-axis. For section 1, we shall take 150 times 20 cubed over 12. And then because of the theorem of parallel axes, we shall add area of section 1 multiplied by the square of distance from its center to the centroid of the entire section, which will get 364,000 millimeter power 4. And then for section 2, we shall have 7.5 times 200 cube. We cube what is perpendicular to the axis of reference, plus area into bracket square of the distance from the center of that section being considered to the center of entire section. We get 5 million millimeter power 4. And then I-axis3, that is moment of inertia of section 3, will be 150 times 20 cubed over 12, plus area, which is 150 times 20 into bracket. Y3 we said is 10, that is 20 over 2 minus 120 square, we get 364,000 millimeter power 4. And now the total moment of inertia of the entire section, we add all of them, which we will end up with 778,000 millimeter power 4. The same case, we use the equation that stress is equivalent to moment multiplied by the distance from the central axis or neutral axis divided by moment of inertia. So if we substitute for steel, you've been given as 150, we will end up with the moment of 97.25 kilonewton meter. But for simply supported beam carrying UDL, we know that maximum moment is WL squared over 8. So M is 97.25, which is equivalent to W times 3.5 squared over 8. Hence, W is 59.83 kilonewton per meter. Now, for the case of timber, it was 59.3 kilonewton per meter, and for the case of steel is 59.83 kilonewton per meter. Now, what we do, we normally adopt the least value of the two. We can now conclude and say, hence, the safe load to be subjected to the composite structure should be a UDL of 59.3 kilonewton per meter. I hope you've enjoyed. Like, share, and subscribe to my channel. See you later. Thanks.